Hi, good morning. We are C4RT and we are 100% of a project that is named Startblock. We are proposing a robotic solution for a process that is made manually. Using robots, we can fetch, manage, deliver, retrieve items for example, for restaurants, hotels, warehouses, libraries, or labs, like here in the DIX.
Our solution actually consists of four main components. So the first component is storage, while the Kinova robot arm will sort and get the items available in the stock area. Then the transport part, while the fetch will deliver items between users and the stock area. And then in the back end, the decision engine will distribute its system and plan the action pipeline. And finally, the interaction between users and the fetch will be through our website. So here's the impact of our solution. It's basically a brief comparison between the current solution and our solution. So the current solution is manually made by employees, while our solution is automated. So users in the current solution will ask staff to provide the service. In our solution, we'll provide users will actually do everything automatically, and the availability will be like 24/7 in our solution. So the experience of a flow diagram. First, the user will place the order through a website, and the decision engine will send the request to Kinova to sort the items, and then Fetch will take that item and deliver it to the users. And when the user is done with using the item requested, it will put it back like in the bench, and Fetch will come back to take it back to the stock area.
Alright, since you guys already see the user flow diagram, and we are moving to our working prototype. So this is an image of our working prototype, which involves a fetch mobile manipulator and the Kinova arm. And here is a video of our prototype working. Alright, so here's the user that is sitting at the bench table in the lab, placed the order on the web app. Kinova now sorted the stuff into the tray. Okay, it is using computer vision to do the pick and place. After the tray is sorted, Fetch will try to grab the tray from the bench table, which is like our storage area. It will scan, look around, and make sure it did not collide into anything. It also keeps the drawing angles. It did not flip the tray over to dump stuff out. Now Fetch is navigate to the benches. And it uses like a visual stem using this little head camera that is on the top that we added to the Fetch. And as you can see, there's markers all over the place. Those are used for recalibration to increasing the accuracy of the navigation set. After the user has finished using stuff, the user puts stuff back into the tray and made a checking request. Then Fetch will come over and grab the stuff. There's no contact directly between the checking process. Fetch will also scan the environment, grab the stuff, tuck the arm, and all go all the way back to our storage area. And it's pretty much a reverse process from this point. So as you can see, Fetch put the tray back onto our storage table, and after that, our Kinova arm is picking stuff out and put them back onto the storage shelf. Alright, move forward to our system diagram. The first one is our system topology diagram. So those are the main components that we have. So in the middle is our decision engine. On the left, there's the physical remote robots, the Fetch mobile manipulator, and Kinova arms. And on the right-hand side, this is our web app. They all internally using gRPC service and server and client to maintain a distributed and asynchronous execution. And the request body looks like that. On the Fetch, there's a navigation stack, grasping stack, and on the Kinova side, there's a grasping stack. On the decision engine, there's a planning stack. Right, so let's take a look at the hardware block diagram for the fetch. So the fetch has an onboard computer, a 6 degree of freedom arm, a differential drive moving base, RGB camera. Those are provided by the fetch. Alright, and the Rose T265 is the tracking camera we added to Visual Slam. On the left hand side, as you can see, there's 9 arterial marker map that is laid out in the makerspace that is used for enhanced accuracy of our navigation stack. So move to the navigation stack. On the left, there's the recalibration stack. It has an estimator of the camera post, the base link post, and the robot post. Those are based on the marker map. And on the right hand side, this is the visual navigation stack. Those things in purple is provided by Ross, and those things in green are written by us. This is basically we are using the Visual Slam to estimate the position of the robot in the scene. And they all communicate through those Ross transformations and topics. Next goes to the fetch grasping stack. On the left hand side, there's all the segmentation. Those are implemented in C++ based on the PCL library, which is point cloud. They do plane segmentation, object clustering, and object identification, and 3D bounding box setting. On the right hand side, there's the motion planning stack. We do environment sensing and collision avoidance, reverse, forward, kinematics, and also Cartesian planning. All right, and they all communicate through those cross topic and transformations. Moving to the Kinova hardware setup. On the left, there's the storage bench. We have 12 arterial markers, 6 in the tray, 6 on the table. We have the bench and the tray, of course. And on the right hand side, there's the Kinova arm. This is all provided by Kinova. It's a Rose D410 RGB camera. Alright, and lastly, there's the Kinova grasping stack. On the left hand side, we have the object of localization. It is using OpenCV and Archer to find out where the object is. On the right hand side, we use Kinova API to provide low-level control of the arm and implement a PID controller and trade location estimator to actually execute the the action. Right.
So for evaluation, we tested individual parts of the pipeline that you saw earlier. On the fetch, the first thing we tested was the navigation. So you can see, here's a video pretty similar to what you just saw, with the fetch driving to a set location, and we measured both how long it took to get to the location, how far away it ended up from the desired location, and whether or not it ran into anything as it drove. So you can see, we tested 5 times, it didn't run into anything, and it always made it pretty close. You can see within about a meter or so of the target every time. It took 40 seconds, so probably longer than a person would take to get there, but not super long. We also tested the grasping on the fetch. This is another thing that you saw earlier. The grasping was not quite as successful as the navigation. As you'll see, it's a little bit trickier and it has like more moving parts. So you can see one of the times that it actually failed, and a couple of times it did successfully pick up and place the box, but it smashed it a little bit. And then for the Kinova, we also tested grasping. Let's see, this will work. Here we go. Yeah, we basically measured how often it was able to successfully pick up and then place the boxes into the tray, and then vice versa. You can see it also remove the items from the tray, place them back in the storage zone. So it's actually using these markers as the places where it's going to store and place the items. And we actually tested 5 times. All the times were successful, except for at one point it did freeze and it started moving again once we waved our hand for the camera. We weren't sure if that was related, but all right, Anand.
Yeah, our solution did handle the problem that it requires human resources to fetch and manage items to the user's interface. It by robotic system as we showed in previous part, with less human involved, more accuracy and faster speed. So in the long-term development, we could be of lower cost, industrial upgraded, supporting more availability and fit into different environments. So for future upgrading, we have planned several steps, including object vision, storage system, and trail design, adding sorting stations and more sensors for different interactions, designing new UI, improves lab and route planning algorithm, and create new pipeline for the route package. And we have also designed metrics for the upgrading next page. For the hardware, the product should be robust, good looking, low noise, and long endurance. And for the software, it should be motorized, fluent interaction, data-driven, and more intelligent. So to accomplish our goal, we need people with skills and experience, including supply chain manager, industrial designer, B2B sales manager, and we also need more resources, including factory for manufacture, and financial support, and business resources. And last, we have some potential APIs to play. First, the fetch and transporting algorithm. Second, the delivery system. And third, the trail design. They could all be applied to manufacturing.
Here's a summary of our budget, and we have spent about 15% of the money we have available. Then we have the project management.
One technique that we used that we enjoyed and helped us a lot was daily stand-ups to keep it up to speed with what the rest of the team members are working on. That's our presentation. Thank you for listening.
The robotics elements are awesome. It's so good to see that. I'm still curious about just the, not the unit economics, but the economics in general. If you compare it, you had a little bit of a breakdown of time spent and everything. If you were to compare it to the status quo or the human counterpart, what the delta would be, over a person. Especially if you can cheat a bit and use the fact that this can work 24/7, so you can use an integral approach where you don't it's crazy pre-prep time or pre-processing time for whatever the action is. And then just looking at what that use case would look like. Because I think in general, the technology is awesome. There's no question about that. But on the adoption side, especially if you have daily stand-ups, to me the missing part is daily stand-ups without a customer or basically someone in the loop. They are massively less useful for me. As far as, you've got to get your primitives have to work, the engineering side. But without understanding what your killer or top use cases are, especially when the economics are awesome, where it's way better to go with this, that to me would be kind of the missing piece. I know it's still early, so that's okay, but in general, having that eye on what that is earlier versus later, I think will save a lot of trouble, a lot of pain as far as what the top 5 or top 10 use cases are, or even top 1.
Hey guys, great to see the progress from, what was it, 3 weeks ago, or, yeah. I probably should have brought this up the first time around, but it seems to me, I'm completely guilty of this, I'll be the first to admit. It seems like you guys are tackling 2 or maybe 3 discrete projects, and it's extremely ambitious. I really like what I see, but it seems like you touched on it on the IT slide, right? There's like a fetch, like a picking portion of this. There's a delivery portion, and it seems like if you were able to focus on one of those and really drill down and bring that to a high level, I think that might be more impactful. That you guys are trying to take on a whole lot, which is cool to see, but I feel like you're only able to make kind of an incremental progress on kind of across the board and trying to move a bunch of pieces forward. So I guess my question to you would be, if you had one thing to focus on, what do you think would be the most valuable or the most interesting or perhaps that has the most room to develop? That might be an interesting way to think about this, moving forward. I do see that you guys are taking the approach of using a lot of things that are already available, right? You're not trying to build everything yourself. You're really utilizing a bunch of components now that are readily available. So I think that's a great approach. But it's really, really interesting to see. Yeah.
Yeah, nice work. It's nice to see that video presentation walk through the end-to-end process. That was well done and nice to see at this point. I still think in terms of your value proposition, you're focusing on automation and efficiency, and I think you need to look at the bigger picture of other applications. And what you might think about is whether you can frame that as not necessarily can this system work faster than a human, but what does this offload to human? And you need a really clear, crisp way to say what that means. And maybe it's transitioning people from task-based work to knowledge-based work, or something that's really quick and succinct and people will immediately get what you mean by that opportunity cost. So that's something to think about. And then last is, I just would love to see you still incorporate some sort of endearing behavior in the system, because at the end of the day, it is, even if it is maybe not a lot of direct human and robotic interaction, the fact is this system needs to exist amongst people and in a context. And if you do that, it's going to make just, the communication of intent, people's ability to work around it or navigate around it, and be forgiving when there is a failure much better, more robust. So maybe that's something you put in your 6-month work.
I'll hold my comments because in the interest of time. So nice job showing the videos were nice. My question on the videos, actually a quick one, is what's the multiplier? How much did you speed up the videos?
That's the video.
For fetch,
Yeah,
it's for the pick and place,
Yeah.
it's 10 times.
10x.
It's really slow.
I need to add to it, like, it is not supposed to be that slow. I think the fetch has a hardware defect there, so it is like the arm motion becomes slow. Before the accident happened, it is actually pretty fast.
So you think it's a safety feature where, that's it's kind
No,
of...
I think
I think it's one of the actuators and having some issue holding, like,
physical damage.
yeah, it's like a physical damage, so
What about the Canova one?
Canova is pretty fast. It's like maybe 2 times.
2x. Okay,
2x, yeah.
great. Awesome. Thank you guys. Corgo, let's come on up.